actuarial science. Dr. Kapoor's notable contribution in actuarial science showcased through published papers and recognized achievements such as a gold medal in M.Sc statistics affirm his prowess. Engaging in research collaborations, he has secured prestigious research grants, including DST SUR-funded project on groundwater depletion. An active member of professional organizations, Dr. Kapoor's commitment to education is evident through his participation in national and international conferences, workshops, and seminars. He has organized significant academic events. Actually, he is also organizing a member coordinator of this, one of the coordinator of this event also, FDP, which we are participating in. In summary, Dr. Harmanpreet Singh Kapoor stands as a dedicated academician and researcher, making a substantial contribution to the mathematics, statistics, and actuarial science. So, with this brief introduction, now I request to Dr. Harmanpreet Singh Kapoor for his lecture to share with our learned participants. Dr. Harmanpreet Singh Kapoor.
Thank you, sir. Thank you, sir. Thank you, sir. Thank you. So, good morning, all of you. So, my voice is audible today?
Yeah, very much audible, sir.
Okay,
Yeah.
thank you, sir. So I'm going to start my today's session. So regarding yesterday, so can you give me the access of host so that I can share my PPT?
Yes, sir, it's already given.
I think it is showing. Okay, now it is. Okay. So regarding yesterday's session, I already have prepared one session for you, and I think you got my recorded lecture or not. Can you tell me whether you have received my recorded session regarding yesterday's session, EDA?
Dear
Yes, sir, we have
participants.
received.
Yes, sir.
Yeah.
Okay.
We got it, sir.
Okay, thank you. So how many of you have gone through that session? Because if you have gone through that session, then we will also cover that coding part for that session today, if I will get time some for that. Okay, so today my topic is that we are going to discuss about testing of hypothesis. That is again a very beautiful topic. That is very also important one when we are doing any you can say statistical analysis. So before going to start the topic, that I want to discuss with you why we have to cover this topic. It means what is the importance of this topic. Give me one. Okay, so yesterday I have discussed with you that we have a major branch of statistics. Okay, and we have further two categorization. That one is called descriptive one, and second one is called inferential. Okay, so in the descriptive statistics, but then first I'm going to tell you what is the difference between descriptive and inferential. So when we have some data set with us and we just want to summarize that one, that means whatever the information that is given to us, we just want to get the information from the data set that we have only. And but in real life, what happen is, let us suppose you want to conduct a survey regarding you want to conduct a study or survey regarding how many persons are affected or diagnosed with a particular kind of disease. So the thing is that you are not able to you are not able to collect the information from each and every individual that is present in the population. So what we generally do is we consider some portion of the population. Here the population is that whatever those individuals who belongs to that particular kind of disease, that individuals will become a part of the population. So for a particular objective, whatever the objects or individuals belongs to that you can say group, that become your population. And when we are considering a portion of that population, that is called a sample. Okay, so it means that when we are not able to fetch or extract or collect data from the entire population, we have only access to the sample observations. And from the sample observation, we have to conclude that whatever the result we got from the sample, whether that result can be generalized to the whole population. For that, we go with the concept of inferential. So in the inferential statistics, what we generally discuss is that we have some limited information given to us, how to extract the information from that sample that can be generalized for the whole population. So under that, we have two branches further in the inferential statistics. One is called estimation, and second one is called testing of hypothesis. My voice is clear today, right?
Yes, sir. It's very good.
Okay, fine. Thank you. So now, what do you mean by estimation here is that I already told you that I'm interested to observe. For example, I'm going to change one example here, that let us suppose I want to know that how much monthly what is your monthly expenditure. That means how much money you are spending on your uh, for on your daily basis, right? So let us suppose I consider that value that I'm interested to observe that what is the mean expenditure, how much money you're spending on monthly basis, right? So for that, I have that means in the population, we have 1 lakh persons. Okay. We have 1 lakh persons in the population, for example, but I am not able to collect information from the entire 1 lakh observation. I have only access to limited number of observation, can be 1000 or 100, right? So based upon this 100 observation, I'm going to make a statement that what is a monthly expenditure, that means on average basis, what is the monthly expenditure of these 1 lakh persons, right? So I'm assuming that mean is my parameter that I'm interested to find it out. Okay. So what I do is I collect the information from this 100 observation and then derive the mean value corresponding to this 100 observation. And I'm saying that this mean value, that is summation of all the that means expenditure of these hundreds observations and divided by the 100. Okay, this shows that xi shows the expenditure of these 100 persons, and I'm summing them and divide by 100. So this is called an estimate, sample estimate for the mean. And I'm trying to say that this x bar represents my population mean. So this is called technique of estimation. So what I'm doing here is I'm taking a sample and I'm implementing some statistical measure over that. And whatever the value I got, I am saying that this value represents or estimate this population parameter. So now in the second case is that we are not estimating the parameter here, but we are going here in this testing of hypothesis. We are making a statement. So here I'm making a statement that my mean is something like $1,000. It can be $10,000 or $1,000. I'm making a statement from on my behalf, and based upon the sample, I'm going to prove this statement, whether this statement is true or false. So this is the concept of testing of hypothesis. I think the idea is clear. The first thing is we have limited number of resources and limited number of observations we have, and from those observations we have to make a statement about population parameter. And there are further two categories. One is called estimation, the second one is called testing of hypothesis. In the estimation, we are deriving the statistical measures from the sample observation. Okay, and in the testing of hypothesis, we are not deriving first. Okay, we are making a statement on our behalf, and based upon the sample observation, we are going to conclude that whatever the statement that we have given, that is correct or incorrect. Okay, so now I'm going to formally start definition. I think the PPT is clear, easily visible to all of you. So the primary objective of statistical analysis is to use data from a sample. That means we have a sample, right? And to make inference about the population parameter from which the sample was drawn. So here the population doesn't mean that we are only talking about that numbering of how many persons we have. Population here means whatever the objective we have defined. Okay, all those objects, all those living and non-living items that belongs to that group, okay, that corresponding to our objective, that part, that become a population. So here you can see that we have some few notations like if someone wants to know that how many students we have, that those are preparing for any competitive examination, and so we are interested to find their mean and variance, right? So this mu is a notation that is used to represent some mu, that is mean, and sigma is a notation that represents the standard deviation. And yesterday in the yesterday session, I already have discussed that to observe the variability among the observations. So we have a standard, we have a measure of dispersion under which we have one measure that is called variance, and second measure is called standard deviation. So this notation X bar, that represents the mean of the sample observation. So do not make confused that we are also deriving the mean here, we also deriving the mean here. The only difference is here is that X bar is the mean of the sample observation. And we are trying to say that whatever the mean we got here, whether that mean is equal to this parameter mu or not. Okay, whether we can say that whatever the sample mean we got from the sample observation, whether that value can represent the population mean or not. In a similar manner, that's small s is the notation for the sample standard deviation, right? And here you can say that this is used to represents the whether this s is good enough so that it represents the population parameter sigma or not. Okay, so now I'm coming to the formal definition of hypothesis testing. What is hypothesis testing? A hypothesis is an educated prediction that can be tested. So like if we make any statement, so we whatever the statement we make, so we have two statements. One is called null hypothesis and second one is called alternative hypothesis. So let me tell you what the difference between this null and alternative hypothesis. Null hypothesis is that we are making any statement that this thing is equal to this thing. So if we are making a statement that mean of this mean of the mean expenditure of any group, that means we have taken the in the example, so that is equal to, for example, 100 or 1000. Okay, so in the alternative hypothesis, whatever the statement that you have made here, right? So we will take other options, alternative options. That means if equality symbol is there, so it is possible that mean can be greater than 1000, it can be less than 1000, or it can be not equal to 1000. So whatever the statement that we have constructed in the null hypothesis, we will consider the opposite of that statement in the alternative hypothesis. So a hypothesis is an educated prediction that can be tested. So why we are saying educated prediction? So because in generally we talk about whatever the statement we make, that means we are talking about a statement about testing of mean, testing of standard deviation. So that can be only be written if there is a possible test statistics available for that can be used for the testing of that null hypothesis or alternative hypothesis. So a hypothesis is a proposed explanation for the phenomena. Okay, so this definition is taken from Wikipedia, and hypothesis is used to define the relationship between two variables. So in the example that I have taken, that means I am only observing one group, and I'm saying that there is one population is with me, and I have one sample observation. That means I have taken one sample from that population, and based upon the sample, I want to make a statement that whether this population mean is equal to 1000 or not, right? So it is also possible that if we have two different populations and we want to make a comparison among those population mean, we can also do that. So in this testing of hypothesis, we have testing for mean, for testing for one sample, testing for two sample, testing for more than two sample also. Okay, so a hypothesis is supposition or proposed explanation made on the basis of limited evidence as starting point for further investigation. That is a very beautiful thing. So we start, so the meaning of this definition says that we start with a rough approximation. Let us suppose I am saying that mean of the population, that means mean expenditure of the population is, let us suppose it is equal to 1000. Okay, so this is a rough statement that I'm making, and I'm going to test it whether that statement is correct or incorrect, right? So based upon the sample observations, I'm going to test it whether that statement is correct or incorrect. And if that statement is not correct, then I go with this possibility. It can be not equal to, it can be greater than, it can be less than. Then if you want to do further analysis, what we can do here is you can modify your null statement again. Now you can, in spite of assuming 1000, you can start with 900, you can start with 1100. And based upon that, based upon the sample observation, we again going to test it, whether that statement that I am making again, that is correct or incorrect. So in this manner, you can rework again and again to get a final conclusion that whatever the null hypothesis that you are making, that is correct or incorrect. So in this testing of hypothesis, in hypothesis testing, we decide whether to accept or reject a particular value of a set. I already have discussed this, that we are going to test these two statements. That means either this statement is correct or either this statement is correct, right? So whatever the test is we generally frame, we assume that this null hypothesis is true because we have equality symbol. So whatever the test statistic, whatever the formula that we assume that in that we put this value. That means we assume that this is the true value that we are assuming, and based upon the some criteria, we are going to conclude at the final state whether the statement that we have made, that is correct or incorrect. That is called correct conclusion. That means we come to that how to conclude it, whether that statement is correct or incorrect. Of particular value of a parameter or those are several parameters. I already have discussed that we can test for one parameter, we can test for more than one more than one parameter, and it is also possible that we can test more than two groups or three groups also. So it is seen that although the exact value of the parameter may be unknown, why we are saying that is unknown? Because as already explained at the initial stage, that when we talk about this population, so we do not have complete information about the population, right? So I do not know what is the exact value of population parameter mu, because I have discussed with you that there are some notation that we have reserved for the population, and there are some notation that we reserved for sample. So if I'm saying mu is the mean for the population, then and I know that I have only access to the sample observation, I do not have access to the whole observations in the population. So that's why I have these values are unknown. That is, mu is not known to me, and sigma is sometimes is not known to me, right? So due to this thing, we have to make a statement that what can be the possible values for these parameters. So there is often some same idea about the true value. Sorry, this is often some idea about the true value. The data collected from sample helps us in rejecting or accepting our hypothesis. Okay, so based upon the sample observation, we are going to make a final conclusion whether we are accepting the null hypothesis or rejecting the null hypothesis. In other words, in dealing with problems of hypothesis testing, we try to arrive at a right decision about a pre-stated hypothesis. Okay, so the some terminologies that I'm going to discuss, exact definition of testing of hypothesis is a test of statistical hypothesis is a two action decision problem after the experimental sample have been obtained. That means we have two actions. Either we are going to accept the null hypothesis or either we're going to reject the null hypothesis, right? And we are going to collect the observation from the sample, and the two action being the acceptance or rejection of the hypothesis. Okay, so let us take one example here. So I have one example with me regarding the statistical hypothesis to determine whether the wages of men or women are equal, right? So what we do is we have two groups here. One is corresponding to male and second is corresponding to female, and we want to make a statement that whether there is a whether there is no significant difference among the wages of men and women, and whether they are equal or whether they are unequal, right? So I can assume that null hypothesis, the wages of men and male and female are equal. So I'm assuming that on average basis, there is no difference between wages of male equal to wages of female. And it can be possible that the wages of male and female, they are can be unequal or greater than less than, right? So whether a particular medicine is effective to cure a disease. So how you will include that? So we know that when there is any, when someone is diagnosed with a particular kind of disease, right? So what we generally do is we get the information based upon some medical let me say measurements. Like if someone is facing you can say issue of BP, blood pressure, high blood pressure. Okay, so we can measure the value of the blood pressure through some tools with us, right? So we know that if someone is diagnosed with a particular kind of disease, and if we want to find out, if we want to cross check whether a particular medicine helps a person to reduce the level of blood pressure, right? So it means that if I am saying that earlier my level of blood pressure was mu times a, okay, and that was equal to something value 150, right? So after taking the medicine, whether the level of blood pressure has reduced from 150 or not. So I'm making a further statement that alternative one is that mu is less than equal to 150. Okay, so in this way, I'm going to make a statement. This is that there is no significant improvement by taking that new drug to the person, and the alternative hypothesis is that that new drug will help to reduce the blood pressure level. Okay, so in the same manner, we are going to make a further statement, like we have further examples, like, so if we assume that x follow normal distribution. So yesterday we have covered one topic that is called bell-shaped distribution, right? What is the meaning of this bell-shaped distribution? So when we have very large observation, or we can say when we have some observations that has such type of histogram, that means when we construct a histogram, okay, I think you can remember the definition of histogram from the yesterday session. And when we uh, join the midpoints of this histogram, and this will show the frequency curve, that means density plot of this data set. And if this you can say this curve of this data set, frequency plot of this data set is equal to this bell-shaped curve, then it is generally assumed that our data set follow normal distribution. And in the theoretical part of this normal distribution, that means we have two parameters, one is called mu and second one is called variance. Okay, so here there are two parameters. One is represented as mean and mu, and other one is represented as sigma square. So here in the parametric hypothesis, why I'm saying parametric hypothesis? Because we have these parameters and we are making a statement about the parameters of the population. So here this null hypothesis is equal to mu1 is equal to mu2, mu is equal to mu1, and alternative ones are mu1 is greater than mu1, mu1 is less than mu1, right? So here, as already discussed with you, that we have two hypotheses. One is null hypothesis, second one is alternative hypothesis, and we represent the null hypothesis by a symbol mu naught, right? And it can be used to make statement regarding different parameters. Like we can use parameter mu also, mu1 is equal to mu2, that represents a mean. We can also make a statement regarding population proportion. I will also tell you what is difference between this parameter p1 and p2 and p, what is the notation for p, right? For example, when we talk about proportions, so proportions means that if we have 100 observations, right, and this observation, among these 100 observations, we have some observations that belongs to one category. It can be category 1, and remaining observations can belongs to second category. Okay, so we want to observe that how many persons that belong to this category 1. So if we note down the frequency, so I am saying that 55 persons belongs to this category 1, and remaining 45% belongs to this category 2. So the proportion can be derived as corresponding to category 1 as 55 upon 100. And proportion corresponding to second category is derived as 45 upon 100. Right? So we can also do the testing whether the proportion of these two groups. Okay, generally we in this example, you can easily see that there's a difference between this proportion of these two groups, but sometimes we do not know actually that what is the proportion for one group and what is the proportion for the second group. But based upon the sample observation, we get some idea, but we have to cross check in proper manner whether there is a significant difference among the proportion of these two groups or not. For that, we can also frame this null hypothesis. Okay, and I already have discussed the concept for mean, that how we can do the testing for mean, and we also write down the same null hypothesis for the standard deviation, that is sigma 1 is equal to sigma 2, and we can also do the testing for this sigma 1 square is equal to sigma, so that is testing for variance of two groups. Okay, So we test the null hypothesis directly, and using some formula, some criteria, we are going to make a statement whether we are going to accept or reject the null hypothesis. So there is one example. This example is for one sample case, because we are assuming that our null hypothesis, that means our population parameter mu, has some value 5, right? And we are going to test whether that statement is correct or not. And there is another example for the two sample case in which we have two parameters, that is mu a corresponding to, that means mean value corresponding to group A and mean value corresponding to group B. And the example says that suppose a doctor has to compare the decrease in blood pressure when drug A and B are used. So the example that I have just taken, that is for one drug. Now we have taken a case of two drugs, and we want to see that whether there is any significant difference between these two drugs or not. So one thing you have to keep in mind, that in the null hypothesis, we always use equality symbols. So here we are making a statement here is under the null hypothesis that there is a no significant difference between the drug A and drug B, right? And alternative one is, if we are saying that this drug B is helpful to reduce the effect of disease, right? So we say that mu B is less than equal to mu A. Okay, and alternative one is mu A is less than equal to mu. Okay, if A is more effective one, because generally what happens is that when we have any when someone is affected with particular kind of disease, and that drug try to bring the value within control, right? That's why I'm saying that mu B is less than equal to mu A if B is more B is more effective drug as compared to A. So these are one null hypothesis. So like as already mentioned that the meaning of H1, that is alternative hypothesis. The alternate hypothesis noted by symbol H1, it can be also be represented by symbol HA or H capital A, is the statement that the parameter has a value that somehow differs from the null hypothesis. Sorry. So as I already explained to you that whatever the equation that whatever the statement that we are considering in the null hypothesis, we are going to make a different statement in the alternative one. And the symbolic form of the alternative hypothesis must be one of these. It can be not equal to, it can be less than, or it can be greater than. Okay. So there are different ways of alternative hypothesis, as I already explained to you. So when we have equality symbol in the null hypothesis, there is possibility that there can be not equal to, and this is called two-sided test. And when we have only one-sided less than or greater than symbol in the alternative hypothesis, then it is called one-sided test. Okay, so this is called when we have only less than or greater than symbol in the alternative hypothesis, then it's called one-sided alternative hypothesis. When we have two-sided alternative, it means that we are assuming that not equal to symbol is there in the alternative hypothesis. And corresponding to that, we consider that corresponding to A section, we have one tail test, and corresponding to B, we have two tail test. So this is one example that I'm showing here is H naught mu is equal to mu naught. So alternative hypothesis are mu is less than mu naught, and alternative one can be mu is greater than mu naught. So this is called one-sided alternative hypothesis. And similarly, when we have not equal symbol in the alternative hypothesis, then it's called two-sided alternative hypothesis. Okay. So, so there is one thing we have to keep in mind, that if we are conducting a study and want to test a hypothesis, to test a support your claim, the claim must be worded so that it becomes an alternative hypothesis. It means that if we are conducting any survey, and I want to say that that particular study will be more beneficial for any particular group, right? So we consider that hypothesis in the alternative one, because in the null hypothesis we assume that study will not be helpful, and in the alternative one we are going to say that study will be helpful. That means there is a significant impact of that study on that particular object. In the alternative one, we are saying that study has a significant impact on the object. So the reason why we are considering our requirement, that means whatever we want in the alternative hypothesis, because if the data set supports if our data set supports our objective, that means whatever objective we want to achieve. So it means we are going to reject the null hypothesis. Okay. For example, I'm going to say that if someone is taking particular type of pill that will help to reduce this fever, or you can say if there is any person using some pills to get rid of consumption of alcohol, right? So I can say that consumption of that pill will not be beneficial for the person to get rid of for this alcohol, right? And alternative one is consumption of that pill will help the person to get rid of alcohol. So from the data set, we are going to say that whatever the null hypothesis that we have constructed, if that null hypothesis got rejected, then automatically we can say that our H1 is corrected, right? So based upon that, we can conclude that whatever the pill that someone has proposed to the person to get rid of alcohol, that is effective one. Okay, so that's why it is always prefer whatever the claim we want to prove, we consider that claim in the alternate hypothesis, and opposite of that we should consider only the null hypothesis. So there is one concept that I have already discussed with you, that we have some method or formula that is used to cross check whatever the statement that we have made, that is correct or incorrect, and that statement, that formula is called test statistic. So there are a difference in the form of this test statistic based upon the null hypothesis. If we are testing for mean, okay, mean for one group and mean for two groups, there is a difference in the formula. If we are testing for proportions, so we have different formula. So one has to keep in mind that whatever the null hypothesis we have and what are the parameters we are incorporating in our null hypothesis, corresponding to that we have to keep in mind that corresponding to this hypothesis, this parameters, which test we have to use. Okay, I will tell you the detailed list that under which scenario one can use this test, one can use this test, and correspondingly you have to just remember that what is the test that is corresponding to that null hypothesis and alternative hypothesis. Okay, so now coming to this critical reason, let me tell you that so we are getting some value from this test statistics, and that value is called calculated value of test statistics. So T doesn't mean that test statistics here. T is another distribution. So that is implemented for the case when we have this type of null hypothesis. Mu1 is equal to some constant value. It can be A, B, C, and H1 is mu1 is not equal to A. It can be greater than A, or it can be less than. Okay, and this hypothesis framed under this assumption that our data set follow bell-shaped curve, that is normal distribution, and we do not have information about the population parameter sigma scale. Okay, so in that case, we are going to use this test statistics, right? And now, so we got the value, and this value is called calculated value of the test statistics. Right now, we how to make a decision whether we are going to accept or reject the null hypothesis. For that, we must be aware about the critical reason. So what is critical reason? Critical reasons are such area if our value of the test statistics, calculated value of test statistics, lie in these areas. Okay, then we are going to say that we are going to reject the null hypothesis. I think my point is clear. I'm again going to repeat it. We first derive the value of test statistics from here, that is called calculated value of test statistics, and we will cross check whether that calculated value of test statistics lie in the rejection region. So these shaded area are called rejection region. Okay, and if the value of test statistics lie in this rejection region, then we are going to reject the null hypothesis. Otherwise, we are going to that means we are not going to accept the null hypothesis. Is it clear? Okay, are you with me?
Yes. Yes, sir.
Okay, fine, thank you. So how we will determine this area? So for that, we make an assumption that we have alpha, that means alpha means type 1 error, probability of type 1 error, and we assume that 5% is the reason that we have assumed in the rejection reason, right? So you can see that there is a area is 0.025, here there is 0.025. When you add them, it will become 5%. Okay, generally we assume that while conducting any study, that means conducting or testing of hypothesis, we have to define the value for alpha, that is probability of type 1 error. I will explain the term type 1 error further, but for the time being, you have to keep in mind there is some percentage from this 100%. We have to uh, deduct from this 100%. Okay, whatever the percentage that we deduct, that is called value of alpha, and we keep that value of alpha as a part of rejection reason. Okay, the critical reason rejection reason is the set of all values of test statistics that cause us to reject the null hypothesis. I think the idea is clear again. So if any value of the calculated value of test statistics lie in these reasons, so we are going to say that we are going to reject the null hypothesis. And if our value lie in the remaining 95% reason, we are going to accept or do not reject the null hypothesis. So there are two terms we can you can keep in your mind. We can reject it or we do not reject it. Okay, the null hypothesis. So acceptance and rejection reason in the case of two-tailed test with 5% significance level. So as already discussed with you, that we have assumed that mu is equal to mu naught, for example, and alternative one is mu one is equal to mu is equal to not equal to mu naught. And if we are taking not equal to simple, so we have already discussed earlier that it is a called two-tailed test because we are considering rejection reason on the two side. We right hand side as well on the left hand side. Okay, because there is possibility that mu can be greater than mu naught or mu is less than mu naught. So there are two possibilities that lies in this alternative hypothesis. So we have to test the null hypothesis on the two-sided tails. So that's why it is called two-sided test. So when we have only alternative hypothesis like mu1 is greater than mu naught, then we will test only at the upper side. In that case, this reason should be equal to 5%. That means now here we are taking 2.5% here, 2.5% here. But in that case, we will consider 5% reason. And if our test statistics lie in this 5% reason for this alternative hypothesis, then we are going to reject the null hypothesis. Okay. So the term that I already have explained to you, the alpha, it is also called significance level, is the probability that the test statistics will fall in the critical region when the null hypothesis is actually true. Okay, I'm not going to discuss the core mathematics here. The only thing you have to remember here is generally we assume alpha as 5%, 1% or 10%. Okay, so it means that we generally assume that either in most of the cases when we are going to make when we're going to test the null hypothesis, it can be assumed that alpha can be considered 5%, 1%, 10%. The only thing you have to the main thing that I want to emphasize here is when we want a very when we're doing a testing hypothesis for a very data set that can cause any significant impact on the human beings. For example, if we are doing testing for the drugs, okay, so we want that our error, that is type 1 error, that should be very small. Okay, I will first go further, then I will explain to you what is type 1 and type 2 error, because I already have a separate section for that I will explain to you. A critical value is any value that separates the critical region where we reject or accept the null hypothesis from the values of the test statistics that do not lead to rejection of the null hypothesis. The meaning of this term is that, so here you can see that there are some values, okay, that segregate or separate the rejection reason from the acceptance reason. So these are called critical point or critical value. Okay, so in this bell-shaped curve, we represent this symbol by minus Z alpha by 2 if we are talking about two-tailed test, and Z alpha by 2, because here we know that in this normal distribution, so this is a symmetric shape curve. That means this is bell-shaped curve, so it is already symmetric. So whatever the probability that we have here on the right-hand side of this line, that means this part that I am taking here, that should be equal to the left-hand side. So that's why it is called symmetric curve. Okay, so the critical value depend on the nature of the null hypothesis. As already discussed with you, that when we have testing for mean, okay, we have different form of test statistics, and corresponding that we have different critical values. Okay, because when we are talking about testing for mean for one group, so and the sigma squares are known, then we go for normal distribution. Then the form of the test statistics will be normal distribution. When the sigma square is unknown, then we go for the t distribution, and corresponding that our critical value got changed. So do not worry, when we do some examples that will be more helpful, then we will get a clear understanding what I am saying at this point. So the concept is clear: two tail, right tail, and left tail. Two tail means when we are doing testing for the two-sided, this one and this one, that is not equal to, because we are also testing on the left hand side when we also doing the testing for the right hand side. So in the one tail test, either we testing of alternative hypothesis on this greater than symbol or less than symbol. So that's why it is called right tail or left tail test. Okay, so as already discussed with you, that in the two tail test we have h naught is equal to h1 is not equal to, because we are dealing with two tail test. And here you can see, whatever if the value of the test statistic lie on this region, that part, then we are going to reject it. Also on the right hand side we are going to reject it, otherwise we do not going to reject the null hypothesis. And the right tail test, here you can see that h naught is equal to, always equal to, and because we are testing for the right side, so it should, in the alternate hypothesis we are putting a symbol greater than. Okay, and we are only testing on the right side part. And how you will get this critical value, because we are removing the 5% probability, and whatever the value that is the critical value, critical point, that segregates the rejection region from the acceptance region, right? So we want 95% on the left hand side and remaining 5% on the right hand side. If the value of the test statistics lie in this region, then we are going to reject the null hypothesis. In the same manner, so if we are doing testing on the left hand side part, so we test the null hypothesis on the left hand side. So here, if our critical value lie in this rejection region, we are going to reject the null hypothesis. Otherwise, we are going to accept it or do not reject it. Now, this is very important term that is called p-value. Why this term is important? Because if we are using any software, okay, if we are using any software, and using that software will not you do not have to find out the value of the test statistics, okay, manually, and then cross check from the table, because the values of the critical points are only available on the statistical tables. For example, let me explain this concept in more detail. So here I'm saying that someone is also typing with me, right? So I'm assuming that mean height, the monthly expenditure of group is 1000, for example, and alternative one, I'm assuming that mu is not equal to 1000. Okay, so I know that I have some mathematical formula that is called test statistics. From that I got some value of test statistics. Now I have to cross check that the value of test statistics, the calculated value of test statistics I got from this formula, whether that value lie in this rejection region or not, right? So I have to see these critical points from statistical tables, because these critical points are only be derived based upon the assumption that what is the value of alpha that we have taken. If we are assuming the value of alpha is 5%, so we have to uh, consider 2.5% area here and 2.5% area here. So what value that segregate this 2.5% area from the acceptance region from this side and this side. So we have to see now whether our calculated value lie in this region or this region, right? So we have to first find out the critical points. Okay, but in programming, so you do not have to do this thing. So what we have to do is we just have to use a criteria that is very simple one. So if we are using 5% level of significance, that is alpha value, and from the code you will get only values of p. Okay, and if the value of p is less than 0.05, right, you can directly make a statement that we are going to reject the null hypothesis. The concept is entirely different. You have to keep this thing in mind. What I'm trying to say, I'm just trying to say that. So here we are checking whether our value of test statistic lie in this region or this region, right? But when we are getting the analysis or when we are getting the output from any software, they only provide the values of p value. Okay, and if we are using the value of alpha as 5%, and you just have to cross check whether the value of p is less than equal to 5% or not. And if it is less than 5%, then we can conclude that we are going to reject the null hypothesis. Otherwise, if p is greater than 0.05, then we do not reject the null hypothesis. I think the idea is clear. Hello.
Yes, sir.
Okay. So two-tailed test, now coming to two-tailed test. So this will be more helpful for you to get understanding of this point of p-value. So if the alternative hypothesis contain the not equal to symbol, as already discussed with the two-tailed test, right? And we know that if the value of the test statistics lie in this region, so we are going to reject the null hypothesis. So how p-value play very important role here is because we derive the value of p using this assumption that it is the basically probability that the test statistics is greater than the calculated value of test statistics. So t is the distribution, we can say distribution of test statistics, and if it is coming to be less than 0.01, then we are going to say that we are going to reject the null hypothesis because our significance level is 5%, right? So here we can identify that how one can derive the values of p. This is just a visualization purpose, but do not have to worry about if you just have to keep this in mind. So p value is less than 0.05, then we are going to reject the null hypothesis for alpha is equal to 5%. If alpha is equal to 1%, then you have to just change the criteria. In spite of 5%, you will check it for 1% and so on. So now further we have right tail test. Right tail test means that here we are only testing the p-value on the right hand side, not on the left hand side. Okay, but again the criteria remains same, that we are again going to make a statement whether if p-value is less than 0.05, we are going to reject the null hypothesis, otherwise we do not reject the null hypothesis. Okay, similarly for the left tail test, we cross check the p-value on the left hand side tail. Okay, and again going to make a statement. Okay, so making a decision. I think the idea is clear now. So we first have a hypothesis with us. Okay, it can be the hypothesis corresponding to population parameter mu. It can be the hypothesis corresponding to proportion. It can be the hypothesis corresponding to the standard variance or standard deviation also. Then we have alternative hypothesis corresponding to that parameter. Then we have the form of test statistics under the null hypothesis. Under the null hypothesis means whatever the value that we assume here, equality symbol, we put that value in this formula. Okay, and we got one calculated value. Okay, from this test statistics, right? And we compare this calculated value in the reason that whether that calculated value lie in this rejection part or acceptance part. And based upon that, we are going to make the statement. So we always test the null hypothesis. The initial condition will always be one of the following. We are going to reject the null hypothesis or fail to reject the null hypothesis. Okay. So traditional method again, reject H naught means that test statistics falls within the critical region. That is already clear. So if our null hypothesis got rejected, it means the value of test statistics lie in this region or either in this region. If it is two-sided test, if it is a one-sided test, then either it lie here only or here only. Okay. So fail to reject H naught if the test statistics does not fall within the critical region. I think this idea is also clear. So again, decision criteria corresponding to p-value method. So as already told you that we are going to reject the null hypothesis, that is H naught, if the p-value, probability value is less than alpha, less than equal to alpha. And alpha is the level of significance, and generally we assume that it is equal to 5%. And if the value of p is greater than alpha, then we do not reject the null hypothesis. Okay, that means we accept the null hypothesis. Okay, now this is again very important topic that is called decision criteria. Okay, let me tell you that what do you mean by confidence interval? So confidence intervals mean that so I'm again taking the same example of I have 1 lakh persons in my population, right? And I have taken one sample from that consists of 100 observations, right? So I got one value of mean that is represented by x1 bar, and I know that I do not have an actual value of population parameter that is mu. That's why I'm making a statement about this population parameter. So what happened is I got one value x1 bar. So it can be something like 105 or 106. So when I take another sample from the population, I got another value of x2 bar. So I'm using this notation x1 bar to represent this is my first sample, this is my second sample, and so on. Okay, so I got some different value. So now you can see that, sorry.
Yes, sir.
Hello.
So continue.
Okay. So what I'm trying to say here is that when I take different samples, corresponding to that, I got different values of x1, x2, x1, x2, x3, x4, and so on. So what I want is I want some range. In this range, I want that this population parameter mu lies. Okay, I'm again going to repeat my statement that when I take different samples, then I got different values of this sample mean, right? So what I do is I try to construct a confidence interval, and I'm going to make a statement that I'm 95% sure that two population parameter that is mu that lie within this interval. So L and U L denotes a lower value, that is the lower limit of this confidence interval for mu. U represents the upper limit for this confidence interval. So if our null hypothesis, that means whatever the statement I have made that my population parameters mu is equal to 100, that is tested as true. That means from the above testing of hypothesis, we got this result that whatever the statement that you have made corresponding to your null hypothesis, that is correct one. So it means that this value of 100 should lie in this interval. Okay. Otherwise, whatever the conclusion you got from the test statistics, it should not be correct one. So I think you're getting my point. So if your null hypothesis is correct corresponding to this above testing criteria, and we have constructed a confidence interval that has some different mathematical construction. Okay, so if that value of mu lie, that means it must be there in this confidence interval, then only we can say that this null hypothesis is true. Because the confidence interval estimate of a population parameter contains the likely value of that parameter, reject a claim that the population parameter has a value that is not included in the confidence interval. So they are saying that reject a claim. So if I from the above testing I got the result that this null hypothesis is incorrect. So if I'm going to construct my confidence interval, 95% confidence interval, that means that I'm 95% sure that whatever the value I have, that is lower and upper limit, my true population parameter lie within this interval. So if this null hypothesis is not correct one, so it means it should not have 100 value in this interval. I think the idea is clear. So now coming to the concept of type 1 error, I already have told you that the value of alpha is basically the probability of type 1 error, right? So let me tell you what is type 1 error. So type 1 error means that when we are making a statement, right? So let us suppose I want to buy something from the market. Okay, let us suppose I want to buy a pen. Okay, I want to buy a pen, and I am assuming that pen is not of good quality. Listen to me very much careful. This is very important thing. That I want to make I want to buy a pen from the market, and I'm assuming that the quality of the pen is not good, but actually it is of good quality. So how I can identify that the quality of the pen is good one? Sometimes we used to buy an item just by looking at the you can say texture or features of an item, but when we touch them, when we use them, we found that the quality of that item is very good enough. So this is called type 1 error. That means we are rejecting something, okay, rejecting something, but act on and we are rejecting something, but actually that item is of good quality. Or if I'm assuming that I'm accepting or rejecting the item based upon the quality characteristics, then if we are rejecting some item based upon the quality characteristics, then but actually the quality of that item is very good enough, so I'm making a error that is called type 1 error. So let me tell you, explain through this graph, that this table, that is very effective one. So here I have matrices here in which I'm showing that on this first column, you can see that there's a term that is called written as decision. That means what decision I'm making about a product, whatever decision I'm making regarding my hypothesis, and this is the actual situation that hypothesis consists of. Okay, so what if I'm saying that my decision regarding a hypothesis accepting, that means I'm accepting the hypothesis what I'm making, and actually the hypothesis is true, that means I'm making a correct decision. Okay, if I'm going to buy a pen from the market and I'm assuming that quality of that pen is good enough, right, or good one, actually the quality of the pen is good, that means I'm making a correct decision, right? Sometime we used to buy some clothes just from the, you can say, just by observing the name of the brand, right? And actually if the quality of that item is good one, so that means we have made a good decision, we have made a correct decision. On the other hand, if I reject an item by assuming that the quality of that item is not good enough, but I got to know from my friends that the quality of that item is very good, but I have rejected it earlier, so that means I have made a mistake, that is called type 1. Okay, is it fine? The concept is clear? Okay, and in the same manner you can see that I'm making a decision that is accepting of h naught. Now I'm saying that I'm going to accept any item and accept any statement, but actually that statement is incorrect, that statement is false, that means I'm making a type 2 error. Okay, so sometime it happens that from advertisement we used to buy some items and assume that item is of good quality, but actually that item is not of good quality, that means we are committing a type 2 error. Okay, and sometime it happens that we are rejecting an item by assuming that item is not of good quality, but actually the item is not of good quality, that means we are making a correct decision. So I think the concept of type 1 and type 2 error is clear, and the probability of type 1 error, that how many times we are rejecting a good item, how many times we are rejecting a good item, okay, that is called type alpha, probability of this thing. Okay, and the probability that how many times we are accepting a wrong item, the probability of this type 2 error is called beta. Okay, so I think this concept is clear to you. So our main objective is we want to control this type 1 and type 2 errors. Why so? Because we do not want to reject a good item and we do not want to accept a wrong item. So that's why we want to control these two errors, alpha and beta. Okay, so what we generally do is, if we want to control one error, then it may lead to increase the other error, so we have to keep uh, balance between these two error values. So for any fixed alpha, that means for any fixed value of probability of type 1 error, an increase in the sample size will cause a decrease in the beta also. But for example, now let me tell you that how we are going to cover this thing. So I have taken an example that I want to buy a pen from the market. So to cross check whether the quality of that item is good or not. So what I do is I also encourage my friends to buy the product from to product of same company. That means to buy pen from of same company, and then I want to note it down their responses. Okay, so now earlier I have made a decision based upon only of my decision. That means I have made a decision only on my opinion. Now I also get opinion from my friends, right? Based upon that, when I increase my sample size, it means earlier I have only n is equal to 1. Now I'm increasing the value of n is equal to 2, 3, 4, and so on. So that will help me to reduce the type 1 error or type 2 error. That is probability of type 1 error and probability of type 2 error. Okay. And if I'm not able to increase my sample size, that means earlier I'm not able to change it, then I have to decrease the probability of type 1 error, and that will increase the probability of type 2 error. Okay. And similarly, if I'm not able to change my sample size, then if I want to, if I'm going to increase type 1 error, that will decrease the type 2 error, vice versa. So it means that probability of type 1 error and probability of type 2 error works in opposite direction. Okay, so if I want to decrease both, then I have to increase my sample size. So what we have covered till now. So we have discussed that how to specify null hypothesis, alternative hypothesis, and we also have to mention that what is the level of significance. That means alpha value, and based upon this alpha value and test statistics, we are going to make a statement whether we are going to accept or reject the null hypothesis, right? And interpret them. That means after accepting or rejecting the null hypothesis, now there is a very important task. That means we know that what we have accepted and what we have rejected. But if we have to make it understandable for the layman person, then we have to write a statement. That means so for example, if any drug is not effective for curing the disease of a patient, so I got this answer that p value is not great less than 0.05. So it means I'm going to reject I'm not going to reject my null hypothesis. So I have to write down this thing in wording also, so that other person can easily understand those things, right? So for example, so we have one example in which we have null hypothesis. A cigarette manufacturer claims that less than 1/8 of the US adult population smokes cigarette. Okay, so if H0 is rejected, you should conclude there is sufficient evidence to indicate that the manufacturer claim is false. Okay, so if you fail to reject H0, you should conclude that there is not sufficient evidence to indicate that the manufacturer claim is false. I think you're getting my point, what I'm trying to say. So accepting or rejecting is for us. That means because we are doing the analysis, but for other person who do not know anything about statistics, we have to give them a correct interpretation of the output. That is very important. So now onwards, we are going to start discussing that under the case of testing for mean under certain assumptions, which statistics, what is the form of the test statistics, and how we are going to make a decision. So for that, you have to keep in mind that what is a null hypothesis, what assumptions we need, what is the form of the test statistics, and how we are going to interpret it, right? So for testing of mean, so you can read from the statement, inference on the mean of population variance known. So we have this null hypothesis testing for mean for one sample. Okay, so I am assuming mu naught as a constant value, and alternative one can be mu is not equal to mu naught, mu is less than mu naught, or mu is greater than mu naught. Okay, so we are assuming that our population is coming from normal distribution, and our variance is known. That means sigma square is given to us, and for that we have this form of test statistics, right? So I'm not going to discuss the construction part of this statistic. You just have to remember that in the case of this hypothesis and this assumption sigma square is known, we go with the normal test statistics, or jet test, you can say. Okay, so this is the form of the null hypothesis, this is the form of the alternative hypothesis, and the test statistics is this one, right? And now, because we have two-tailed test, as already discussed, that when we have not equality symbol, it means we have a two-tailed test. So we are going to test either on the left-hand side or either on the right-hand side, right? If the value of test strategy lie on the left-hand side of minus z alpha by 2 or on the right-hand side of z alpha by 2, then we are going to reject the null hypothesis. And if the value of the test statistics, this one value, z naught value, lie within this region, then we do not reject the null hypothesis, right? So you can see from this graphic representation also, in the two-tailed test, we have this rejection region, right? And one can also derive the p-value by using this formula. Okay, I'm not going into detail how one can derive it, but if you're using any software, that means in the software, these values are given to you directly. You just have to observe that if whether p-value is less than 0.05, if you're assuming alpha as level of significance 5% or not, and if it is greater than that, means we are not going to reject the null hypothesis. For the upper tail test, we cross-check the critical region, cross-check our calculated value of test size on the upper side, and for the less than lower tail test, we cross-check our value of test ratio on the lower side. Okay, so this is the summary that you can see for the testing of alternative hypothesis when it's not equality symbol is there. We are going to cross-check on the both sided, and when we have upper tail, then we cross-check on the upper side. When we have lower tail, then we cross-check on the lower side. So now, as already told you that we have type 2 error, that means probability of type 2 error is noted by symbol beta. And if someone wants to find out, one can easily derive using this method also, right? And this very important topic that is called, sometimes it is required that we want to identify how many observations, what is the sample size that is required for conducting any study. Okay, so this is a formula that helps to identify that if we have the value of type 1 error, probability of type 1 error is given to us, probability of type 2 error is given to us, and we have also this information that there is a deviation of population parameter from its mu naught, that is assumed value, and we have to identify the value of n, that is sample size. That what is the sample size that is required under this scenario, then one can derive this value using this formula. Okay, so this example shows that if a value of sigma is given to you, sigma is equal to 2, and there is a only 1 unit difference between the population parameter mu and assumed value, and we assume that alpha is equal to 5%, that is probability of type 1 error, probability of type 2 error is 10%, and then we need a sample size of 42, then only whatever the analysis we do, that is fruitful. Okay, because sometimes it is required that how many observations we require to get a very good results. So that's why this formula is helpful in that scenario. But the thing is that you must be aware about that whatever the assumption that you are making regarding the population parameter, you must be known in advance. Then only you can derive these things. Or you can roughly estimate that if I'm making an assumption that my population parameter is equal to something, and based upon that, how many sample size I required. So one can derive those values. Okay, and this thing will help you to understand that for increase in sample size, because we have discussed that how to control type 1 probability of type 1 and probability of type 2, that is alpha and beta. So there is one possibility is that you can increase the sample size. If you increase the sample size, then both alpha and beta got decreased. But when we have fixed number of observations, right, that means if n is equal to k always, then if you want to increase the alpha, then beta got decreased, and if you increase the value of beta, then alpha got decreased. So they behaves like in the opposite direction. So using this values, you can see that if we assume a sample size of 43, the power is 90%, the power is again 90%. So what is power? Power is 1 minus beta. Okay, so whatever the value of beta we have, so if we subtract that value from 1, whatever the value we got, that is the power of the test. Okay, So you can see that when we have small sample size, your power got decreased, right? When we have small sample size, your power decrease further. So the meaning of power is that how efficient your test statistics is to identify the difference in the true population parameter. That means we had made assumption that mu is equal to 50, right? So we want to cross check that whatever the criteria that we have adopted, whether that criteria is able to identify that whether your mu is actually equal to 50 or there must be some variation of value of mu. So this is called a power. Okay, for large sample size, let me tell you the meaning of this thing. Large sample size means generally we assume that for large sample size, every test follow normal distribution. So this is the requirement. You have to keep in mind that for that we need at least 30 observations. Then we can only say that we can go for parametric test. That is the we can assume that our data set follow normal distribution. Okay, so it means there are among this above given 5 criteria, there are only 3 important criteria. You must know how to identify the null and alternate hypothesis, and based upon the alternate hypothesis, you can identify whether it's a two-tailed test, whether it is a one-tailed test. Okay, and after that, we have to see which form of test statistics we are going to use, whether we are going to use Z test, whether we are going to use T test and any other criteria. And after that, we have to see how whether our value of the test statistics lie in the acceptance region, rejection region, or not. Or from the p-value also, you can make a decision whether the p-value is less than equal to alpha, that is level of significance, or if it is greater than equal to alpha. Okay, and based upon that, you can make your statement. So this tables, that means you can, in this table, you can easily see that when we have large sample size, okay, so your power got increased. Okay, and also you can see that with the large sample size, your power got increased and the value of the p, okay, that also is very small. That means p is less than 0.00010 power minus 50. It shows that it is very close to 0. So it means we can easily say that if your actual value of mu is 50.50, for example, and you got the value of x bar as 50.50, okay, that means this is a sample value and this is a population value, right? So it may possible that with small sample size you're not able to identify that there can be other possibility of for the value of x bar, and we're accepting the null hypothesis. But when we increase sample size, you got to know that for one sample you are getting accidentally the value of x bar equal to the population parameter mu. But when you change the sample size, it may possible that your true population parameter value, that means x bar value, should not be equal to the true population parameter value. So one can easily identify those things when we increase sample size. And here we got this result that we are going to reject the null hypothesis. Okay. So inference on the mean of the population, variance known, as already discussed further. Let me come to this concept of confidence interval. Okay. So as already told you that in the confidence interval, what is our main requirement is that we want to find a lower and upper limit regarding the population parameter. And we want to say with some confidence that our true population parameter lie within this region. So alpha is, let us suppose it is equal to 5% level of significance, then it is equal to 95%, this value. So we can say that I am confident that 95% the population parameter mu lie in this interval. So this probability is the you can say confidence, or you can say it's just you can say it's a probability that shows that population parameter mu lie within this interval. Okay, so if someone wants to find out a lower and upper one-sided confidence interval for lower and upper case, then these are the formulas. Okay, and this table shows that when we change the confidence interval on the mean corresponding to simulation, that means once we are getting this range for the confidence interval for one simulation, this is the range of the confidence interval for second simulation, then its shape should be of this form. Okay, so now coming to this I think I should go ahead because I already have explained the concept of confidence interval to you. Okay. So this is a method one can construct the confidence interval for the parameter mu. So this is general term I already have explained, because I want to discuss another test also. I'm very much I'm lacking of time, so I'm going to skip those things. Those already have discussed with you. So now, if we assume that L and mu are the lower and upper limit, okay, then one can derive the confidence interval for those uh, for those parameter theta using this method. Let me show which one. Okay, let me explain to you. I think I have skipped those part. Okay. So how one can derive this thing? So I am putting L is the lower limit. Then I have to put this value of L here is represent the value of the test statistics here. L plus minus that Z alpha by 2. If I'm deriving the confidence interval for mu, then it is X bar here. Then the value of sigma upon square root of L. What I'm trying to say here is that X bar minus Z alpha by 2 sigma upon N will become your L value. Okay. And X bar plus Z alpha by 2 sigma upon under root N will be your U value for finding the confidence interval for parameter mu. So in this way, we can easily understand that if any value lie in this confidence interval L or U, okay, so we can, if we want to test that value of any parameter mu naught that lie in this interval, then if we are making further a statement regarding that population parameter, then it should be correct one. For example, if I'm getting a confidence interval as 110 to 150, okay, for the population parameter mu, right? And I'm going to test that my population parameter is 125, for example. Then based upon the same sample, that I have with me, I got the answer that I'm not going to reject the null hypothesis. So this is the only thing that I want to emphasize here is that one get whatever the confidence interval we got using this formula, we got the same conclusion. If we are going to test any value in between that confidence interval and do the testing of hypothesis part. So this is the beauty of this relationship of testing of hypothesis and confidence interval, that the conclusion from both the parts, they are equal, right? And this is very important thing, that if someone wants to identify what is the width or confidence interval, then what we can see here is this part and this part together become the width of the confidence interval, right? And this is again a method that is used to find out the sample size for any study. That means if we want to conduct a study and we want to assume that what is the sample size that is required, for that we can use this method, that we can take the width of the confidence interval for the parameter, and from that we can derive the value for the sample size. I think this idea is clear, that if we are assuming the formula for lower limit as this one that I already have written above, this is the formula for finding the upper limit, and we are assuming that there is some term error that shows the difference of X bar is from its true population parameter value. That means there is a variation between the sample mean from its population parameter mean. And if we want to find out what is sample size that is required under this situation, then this is the formula. Okay. And why this topic is important, that why derivation of the sample size is important, because let us suppose if we want to conduct a study, right? So we know that what our population is this group, for example, but we do not know that how many samples we have to take. We can't take randomly any figure at 50, 20. We have to go with some proper steps. That means we have to follow some criteria. Based upon that, we got to know that this is the required sample size that must be important for conducting any studies, and this is the formula for that. Okay. So confidence interval, this example here to illustrate the use of this procedure. Suppose that we want the error in estimating the mean burning rate of rocket propellant. to be less than 1.5. So this is example in which we are considering the case of rocket propellant, and we want that the difference between the actual value of x bar and mu is less than 1.5 with 95% confidence. And with this given value of sigma s2 and this value of z we got from the statistical table. And now you can see that after putting all those values, we got that we need sample size of at least 7. Then only we got an answer that the difference between x bar and population parameter is less than equal to 1.5. Okay, so this is the thing you are able to understand that why this construction of this requirement for determination of sample size is important. Okay, I'm skipping this part because this is the general formula finding out the confidence interval. So here you can see that this is the lower limit of the function of test statistics, the upper limit of the function of test statistics. This is the parameter theta. It can be mu, it can be sigma square, it can be another parameter p also. So now the next topic, there is a difference here is that in the previous topic, we have assumed that we have population parameter h naught, mu is equal to mu naught, but earlier we have this assumption information given to us that sigma square is known, right? But here we do not have this value sigma square. So it means we have to change the form of the test statistics. The idea is clear, the difference is clear. We have the same hypothesis, mu is equal to mu naught, mu is not equal to mu naught, or mu is greater than mu naught, or mu is less than mu naught. But there is one information that is missing here is that earlier the information is given to us that variance is known, but now variance is unknown. Now variance belongs to the population parameter. The sigma square belongs to population. So in real life, we do not have that value also. So in that case, we are not going to implement Z test. Now we are going to implement T test. For the testing of hypothesis for one sample case, for testing of hypothesis of mean for one sample, now we are going to go with the T test. And the mathematical form of T test is this one. Now again, the criteria is same. This is the form of the test statistics we calculated, and that is called calculated value of T test. And then now further, we are going to cross check whether that value of test statistics lie in this rejection region if we are talking about two-tailed test. And if we are talking about one-tailed test on the upper side, then we are considering 5% region here only. And if we are talking about low tail test, then we consider 5% region here only. If the value of test statistics lie in this region, then we are going to reject the null hypothesis, and otherwise we are going to do not reject or accept the null hypothesis, right? So in this graphical representation, I'm going to show here is that the shape of the T distribution is again similar to the normal distribution. The only difference here is that this T distribution is more peaked, and when we increase the sample size, there is no difference in the distribution of normal and T distribution. Although this thing is not directly be relevant to you, but for understanding, someone wants to read about the concept of T distribution, that with increase in sample size, the properties of the T distribution and the properties of normal distribution, they are almost equal. Okay, like similarly, I have discussed with you for the two-tailed test. Now we have the value of critical point from the T table, and this is the lower value of the test statistics. Let me a lower value of the critical point, and this is the upper value of the critical point. And if our value of test statistics lie in this region, we are going to reject it. Otherwise, we do not reject the hypothesis. Okay. So similarly, we have to follow the same criteria like p-value. What is p-value? The same thing. If we are getting the value of p as less than 0.05, then we are going to make a statement that we are going to reject the null hypothesis. Otherwise, we do not reject the null hypothesis. And this thing is valid for both these cases of upper tail and lower tail. Okay. So how to summarize this section? So we have testing for one sample case, and because sigma square is unknown, okay, so we go with the T test, and for two-tailed test we have this rejection criteria. Value of T naught, that is calculated value of test statistics, it should be greater than the upper tail or lower than the lower tail critical points. And if we are talking about alternative hypothesis as one tail test, then it should be greater than. For the lower tail test, it should be less than. Okay. So here, similarly, inference on the mean of the population variance unknown. So we have this graphical representation that how we can get this value of P. Okay, that means these are the reasons where we have rejection reasons, shaded one, and other one are non-rejection reasons. This is the example that one has derived the p-value through software. Now you can see here the p-value is coming at 0.01, here the p-value is coming at 0.05. So both lie in the rejection region for alpha is equal to 5%. Now coming to, one can also construct the confidence interval for the population parameter mu in the case of variance unknown. For that, we have to use this different formula. Earlier, we have a notation from the normal table, that is Z alpha by 2, but here we have the value from the T table. Okay, this thing you have to keep in mind. And if we are doing any, if we are doing programming, then these things are not required. You just have the output from the code. You just have to understand what the meaning of those things. And this thing is required if you are doing, we are solving these things through some, you can say doing manually. That means you're solving these things manually. That for that purpose, you have to remember these formulas. Okay. So I'm coming further. I want to cover one topic of testing of this thing. So this topic, in this topic, we are going to cover testing for variance. Okay, testing for variance of single population. So here you can see that our null hypothesis consists of parameter sigma square, not mu. Right? We are considering sigma square is equal to sigma naught square, and the alternative hypothesis, we are assuming sigma square is not equal to sigma naught square. So you have to keep in mind, in this situation, we go with the chi-square test statistics. Okay, and so it means the form of the test statistics is different now. It follows chi-square distribution, and we cross-check the value of this above x naught square with the tabulated value of chi-square. That means the form of the chi-square distribution of this form, right? And if we are doing testing on the both sides, then we have to cross-check the value of chi-square. So this is positive chi-square alpha by 2. And if the value of the test is lie in this region, then we are going to reject the null hypothesis. Otherwise, we are going to accept it or do not reject it. So this is the mathematical form of the chi-square distribution, right? So you can see the shape of the chi-square distribution as this one. So it is not bell-shaped. One thing you have to keep in mind. Okay, sometimes it behaves like a positive skew distribution. Sometimes it behaves like a normal distribution. For different values of the sample size, the shape of the chi-square distribution varies. So all of you are with me? Hello?
Yes, sir.
Okay.
Yes.
Okay. So I think you're getting the point that I want to emphasize here is that you have to keep in mind that what are the parameters we have in the null hypothesis. Based upon that, you have to define your test statistics, and then corresponding to that, you have your difference in the critical points, and you can make your decision based upon that. Okay. So if we are talking about testing of hypothesis, only testing of this sigma square, sigma naught square, and ultimate one is sigma square is greater than sigma naught square, then we are only going to test this hypothesis on the right hand side, right? So in this case, you just have to observe that where the value of test statistic lies. Okay, if it is lie in this rejection region, then we're going to reject the null hypothesis. Otherwise, we do not reject the null hypothesis. So this is a summary. That means we have h naught sigma square is equal to sigma naught square. Chi square has this test statistics form is of this chi square distributed formula, and rejection criteria is for two tail test greater than less than. For upper tail test, it is upper side. For lower tail test, it is on the lower side. Okay, this is the graphic representation for the same, right? If someone has any doubt, I can stop there and I can explain the terms to you also. Okay. Now you can see here is inference on the variance of a normal distribution. So we know that if someone wants to find out the confidence interval for sigma square. Okay, so what is the meaning of this thing? Again, the same thing that we want to be very much sure that the 95% or 1 minus alpha percent. So if you put alpha is equal to 5%, then it will become a 95%. So I want to be 95% sure that that my sigma scale lie within this interval. Okay, so this is the formula. So one can derive that, and based upon that, you can say that I'm 95% sure that variance or this variance lie within this interval. Okay, now I'm this is the third topic. That means first we have covered testing for mean for one sample. Then we have covered testing for variance of one sample. And in that we have covered two cases. One is sigma square is known, and second one is sigma square is unknown. In third case, we are going to test about testing for proportions. And I already have explained the meaning of proportion. Proportion means that when we have some observations that are given to you in terms of categorical form, and we can only note it down. But it can be absence, presence, it can be male, female, it can be any other category, any other no, you can say binary form data in which there are only two categories. Then we use this term P, that is represent the proportion. And for that, we have this formula as a test statistics, right? So now you can see here is that whatever the value we got from this formula of test statistics, we are going to test it on the normal distributed table. So if the value of Z naught lie on this rejection reason for the two-tailed test, then we're going to reject the null hypothesis that P is equal to P naught. Otherwise, if we have an alternative hypothesis on the right-hand side tail, or right-hand side one-sided test, then we are testing only on the right-hand side. Otherwise, if we have alternative one on the lower side, then we're testing on the lower side. So there is one example. I think this is very important if I should discuss this with you. A semiconductor manufacturer produces controller used in automobile engine application. The customer required that process fallout of fraction defective at a critical manufacturing step not exceed 5%. So what is the requirement? So we want that whatever the item that we are producing, so we do not want to be more defective item greater than 5%. So not exceed. That means we do not want that there are more than 5% defective item while producing any item. That the manufacturer demonstrate process capability at this level of quality alpha is equal to 5%. So the person has assumed 5% level of significance, and they have taken a sample of size 200 and observed that 4 of them are defective. Among these 200, they have observed 4 of them are defective one. So we know that this is a case of testing of hypothesis of proportion because we have 4 defective items among 200 items. So here you can see that X bar, or you can say proportion of P hat, that is X upon N, that is 4 upon 200, right? So we are going for testing for the population proportion parameter P. And we have made a assumption or we have make a hypothesis null hypothesis as P is equal to 0.05 because we want this condition to be cross-checked. So we always assume equality symbol because we want that do not exceed. That's why we have taken alternative hypothesis as P is less than 0.05, right? And based upon the test statistics, whatever the value we got, we cross-check the value from the normal table. And if the value of the that value lie in the rejection region, then we are going to reject the null hypothesis, right? So Z0 we derive using this formula. We got value of x is equal to 4. We have sample of size 200. We know that P naught is equal to 0.05. That is already given to us in the equation. And we put all those values and we got value of Z0 as minus 1.96. And the value of Z0 is minus 1.96 is on this side. Because this standard normal table has mean value 0. And it has negative value on the left hand side and positive value on the right hand side. So now we want to cross check either deriving from the p value that whether we're going to reject the hypothesis or accept it. From the p value, you can see that the value is coming at 0.0256. Okay, and we have assumed alpha is equal to 5%. So as already the criteria already have explained to you that p value should, if it is less than equal to alpha, then we are going to reject the null hypothesis, right? So from here you can see that 5%, this 0.0256 is less than 0.05. So we are going to reject the null hypothesis and say that whatever the you can say statement, that means the person required, that is fulfilled. Okay. And one can also derive the confidence interval for this binomial parameter p using this mathematical relationship. And the concept is very important. Do not consider the mathematical part. Only we have to observe here is that what is the meaning of this confidence interval. It says that if we are assuming alpha is equal to 5%, then this confidence interval will give you a limit that shows that I'm 95% confident that the population parameter p lie within this interval. Okay. And again, for the same problem, we have derived the confidence interval for p. And here you can see that the p is 0.05, is equality symbol is there. That's why is assumption not satisfied, because we assumed p is less than 0.05. And these are the formula if you want to derive the sample size for the case of proportions. And these are the mathematical formulas that I have explained here. Okay. And there is one more topic, maybe you have read somewhere, that is called goodness of fit. So do you know what is goodness of fit? Anyone, any idea from the audience? Hello? Are you with me?
Yes, we are.
So any idea about, so this thing is something different. That's why I want to spend time on that, because I have only 10-15 minutes with me. So I want to cover up this topic also. Okay. So sometime what we need is, there are some variable values are given to us. So I am assuming that x is a variable and it represents the height or weight, for example. Why I'm considering the same observations? Because so that you can easily correlate. So I'm assuming that x represents the height of an individual, right? And I want to say that these whatever the values I have with me corresponding to the 100 individuals, okay, that means their height, that must come from the normal distribution. Normal distribution means I want to say that the shape of the histogram of this data set should be of this format. Okay. So in most of the softwares nowadays, what they do is they cross check that the distribution of this data set, it can be normal, it can be other distribution. So for that case, goodness of fit is very important criteria or method that cross check whether whatever the statement that we are making about the data set, whether it is coming from any distribution, that is correct or incorrect. I think this idea is clear. So far we assume the population or probability distribution for a particular problem is known, right? So what is the meaning that we are discussing? We have assumed that we are testing for mean, we are testing for the testing for mean, testing for variance, testing for population proportion. But if someone wants to know about the distribution of the data set, for that, goodness of fit test is most important. I'm not okay. Let's see. So here, for that case, we use chi-square test. Okay, and the criteria is again same, that we first construct a hypothesis that I'm assuming my data set is coming from this distribution. Alternative one is my data set is not coming from this distribution, or I can say that my data set does not belongs to the distribution A, and here I'm assuming that my data set is belongs to this distribution A or not. So I'm using the test statistics chi-square and from the value of calculated test statistics, I again cross-check. Okay, cross-check that whether my calculated value of test statistics lie in the rejection region or not. If that value of test statistics lie in the rejection region, then I can conclude that whatever the assumption that I made, that whatever statement I have made under the null hypothesis, that is incorrect. Otherwise, I can say that whatever the statement I have made regarding the under the null hypothesis regarding for the observation, that is correct one. Okay, hope the idea is clear to all of you. So I am keeping 5 or 10 minutes for your queries. If you have any query, we can discuss. Hello. So I'm reading the, if there is any comment from the audience, then I will try to address those issues.
Nancy, just speak like that. Sir, kindly check the chat box. I think the queries are being coming there.
Yes, I'm checking it. If there is any particular thing they want to discuss, I'm reading simultaneously. Degree of freedom. Okay. So basically, the degree of freedom means that, so for example, we have that is sorry.
Is life.
Participants, please unmute yourself. Oh, sorry, mute yourself.
Mute, sir, yeah. So basically what I'm trying, so degree of freedom means that when we have any sample size that is given to us, for example, 100. Okay. So there is some constraint over these 100 observations. So degree of freedom is basically n minus constraints. Okay. For example, in the case of T distribution, if you are very much familiar with the term of degree of freedom for the T distribution, so T distribution has degree of freedom n minus 1. Now, in the case of single sample, right? So why so? Because I have already told you in advance that sigma square is unknown, right? That means I do not have the information regarding the population parameter, that is variance. So what we used to do is while solving that formula for the test statistics, we replace sigma square by the sample variance. Okay, so it means we are using estimate of the sigma square. So that's why we are reducing one observation from the total number of observation. So that will become the degree of freedom. Hope this query is resolved. Okay. Any other query?
Sir, good afternoon.
Good afternoon.
Sir, myself, Dr. Harsha Srimatat from Karnataka.
Mm-hmm.
I have a question on significance level, sir.
Yes, sir. Tell me.
First of all, I thank for the very nice presentation for the organizer and also you, sir. And then my question is, uh, sir, when we are testing the significance level 5%,
Mm-hmm.
1%,
Mm-hmm.
and 10%, no? That
Yes, yes,
means
yes.
what, sir? We are testing about the error rate.
Basically, significance, you can see that it is basically alpha, right?
Yes, sir.
Okay, so we are assuming that alpha is equal to 5%, it is equal to 1%, or it is equal to 10%, right? Hello.
Yes, sir.
So now I already explained to you that what is alpha, that is probability of type 1 error.
Yeah.
So what does it mean? It means that by you can say lack of knowledge, we are rejecting anything that is of good quality or that is true.
Okay, sir.
Okay, so it means that when we are talking about a very sensitive case, it means, so that's why I have told you in advance also that when we are talking about any data set that is related to the drugs, that is in the pharmaceutical industry, they always want type 1 error to be as small as possible.
Okay.
Right, that's why they consider alpha as 1%. Sometimes they also consider very less value of alpha, more than less than 1% also. But sometimes when this you can say probability of type 1 error is not harmful for the audience, for the participant, and other case for which we are conducting a study. In that case, we can use 10% level of also 10% alpha level of significance also. It depends, it varies from the objective.
Okay.
Any other
Okay,
question?
sir. Thanks.
Thank you.
Thank you, sir.
Thank you. So if there is any query or question from the audience, just tell me.
Hello.
Yes, yes. Hello, can you hear me?
Yes, sir, you are audible.
Yes, sir.
Dear participant, if you have any more question, please. You can unmute your mic to put your question. Sir, I think there is no more question.
Okay.
You please explain the assignment, sir.
Okay, great. We are waiting for some queries from the participant side. Thank you.
Excuse me, sir. I
Everybody.
have one query, sir.
Yes, you can ask.
Yes, so if we have done some work in this machine learning and we have implemented on some data set and we want to validate our results, so which test is better for the validation purpose? How we can select that test, sir? Can you please
Actually,
explain?
that the thing that you are saying, that is very entirely different. Validation is a different thing, and this testing hypothesis is a different thing.
So for validation, we can't apply these tests that whether to check that what we are doing that is right or not.
No. Basically, here what we have discussed today, we have discussed regarding that how if some parameters are unknown, that means we want to make a statement. So that consists of some parameters. You can observe that we have assumed mean, we have assumed population proportion, we have assumed variance. So validation, so in your machine learning, right, for example, so validation is a different scenario. That means that is taken care in a different manner.
Okay, sir. Okay, thank you.
Sir, I have one more question.
Yes, sir. Yes, sir.
Sir, if qualitative data and quantitative data are different, no? If when data are different, again that t-test and all these are matters.
Basically, we can't implement these tests on the quality data set. We want them to be of continuous nature. This is the assumption that I have already explained to you, that whatever the statistical measures like measure of standard tendency, measure of dispersion, we can only implement on the quantity data set.
Okay, sir.
There are some tests available in the literature. Okay,
Okay.
so
Okay, sir.
whatever thing that I have discussed today, that is only related to parametric testing. I have not discussed non-parametric testing.
Okay, sir.
Okay.
So for qualitative, then we have to apply some other test, or these can also be applied on
No,
the
no,
images, or
we have to go with the non-parametric testing criteria.
okay, okay, sir. Okay.
Haan ji, ma'am. Okay. So basically, there's one question someone has asked me about confidence interval. So for example, confidence interval, I'm going to explain again. So I have the confidence interval is written as 100 to 1 minus alpha %, right? So for value of alpha, if I assume alpha is 5%, so it means it is equal to 95%. So whatever the formula that we have with us, that helps us to say that I am 95% confident that the population parameter lie in this lower and upper limit. Are you able to understand? I think one has asked me this thing. Ibrahim. If someone else has any query, one can ask regarding today's presentation. I will share it. Do not worry about that. Just try to focus on the thing that I have discussed. So Dr. Meher, should we conclude or should we wait for the participant to ask their queries?
Dear Professor, I think we should now conclude the session.
Okay.
Yeah. Dear participant, there is something about you. One thing is all the assignments are mandatory to all the participants to submit in well in time. And the recordings of each session are available who are registered at mattechguru.com. And some of the participants not able to register through this platform. So what we are doing for the other participant, we have developed a playlist on YouTube. All the lectures will be uploaded there, and the playlist has been shared in the WhatsApp group, and from that everyone you can access all the recordings which are being presented during these 14 days faculty. And secondly, the participants who are registered through mattechguru.com, I request you to all, please always join through your account detail by using your username and password. All the assignments or quiz, all the quiz are in the form of assignment from our side. Okay. So some of the participants are asking about the assignment we are not getting. All these are available in your account. Just you need to log in your Mathstech Guru account, and all the details of each we are sharing on your email address. Please check your email very carefully. And some of the participant I checked yesterday, even did not log in the account, and because the participant we have registered till now are more than 300, and I saw that here right now we are 100 plus participant are joining this session, and many other participant who are not able to join, or maybe some other technical issue. So to make accessible everything and each information we are sharing on your email address as well as on WhatsApp group. If any participant have any kind of problem, any issue, please always feel free to contact us. WhatsApp number is there. You can find the numbers of help desk and the coordinators on website, on the brochure, whatever the way you adopt to reach us. Okay, so everything is there. Still, one more thing, some of the participant, I think, not getting the email. This may be the reason that email which we are sending you go to in your spam box. Okay, so please check your spam box also. And there are some few email addresses which we got from your site, which are not correct. That may be some space, or you use other, sometimes we use by default dot at misplaced. Okay, so some of the emails like the data from the data I can access yesterday, these are about 10 to 15 email addresses are incorrect in our database. So the thing is, you can submit when you will submit your feedback form. Okay, please make it correct. And that's why we are sending you emails again and again, so that you can update your email address. And still then, if you are not getting any email from our side, you can reach us, you can contact through email, or you can contact us through WhatsApp, or you can call us. Okay, so all the things may be available for you, and the recordings of each session are available there. And last one more thing, some participant are reaching us to register till now. Of course, you can register, but the thing is, you have to complete from starting to last 14 days. Okay, if today the participant, I saw that today 5 participant register in this event. Okay, still this will be open. So the participant who joined today this faculty development program, they have to cover the previous lectures through login the account. Okay, and submit your quiz and listen all the recordings also. Okay, hello. Without this, if you have any more question, please feel free to ask for me. Yes, my WhatsApp number I am sharing in WhatsApp number in chat right now. Please check your chat.
Okay.
Where is chat? Just 1 minute. Please note, my WhatsApp number is plus 91 97 80 92 0053. So this is my WhatsApp number, and also this is my personal number. You can Indians can call me at this number if you have any kind of issue, and the international participant, you can contact me through WhatsApp or WhatsApp call. Okay, so that all the things, if any kind of issue you are facing, we can sort out. And the feedback form for today's session I have shared in the chat box. You can check it and submit the feedback. The entire session was really very wonderful, and all type of tests which are required for data analysis and for the machine learning, for the prediction, also like t-test, p-test, hypothesis test, and all these are basic tests which are highly required for the beginning. And because the thing is, we know about the formula, but if we are not able to understand which type of test is required to apply for what purpose, this is very important to know the purpose of the use of the test, and the entire information about the test was very clearly. Yes, please. Someone is
Uh,
asking.
Do we have an assignment?
Okay, assignment. We are sharing the quiz in the form of assignment. Okay. If you need some more stuff to study, I have shared one book 2 days ago, and today also we will provide you some more stuff which are supporting this faculty development program. Okay, and I also request to the Dr. Kapoor to provide some more content which are highly useful for today's session and for the yesterday's session, and the PPTs which was used to present during the session will also be available for all the participant in your account, as well as the participant who are attending the session through other media. Okay, or some are not registered on mathtechguru.com, so they will get on WhatsApp or through their email address. Okay, so whatever you have the issue and what are the requirement for the presentation from your side, please always feel free to contact us and tell us which type of challenges from your side are. Okay, and we always try to accommodate with you as much as possible. Thank you. And I think the today's session is really wonderful, informative, very useful to all the participants. So now I am very really thankful to our resource person for this wonderful session, and we are presenting a memento, a certificate of appreciation for this wonderful presentation, is hereby acknowledged and honored for her explanatory contribution as the keynote speaker on the topic of statistical analysis and hypothesis testing at the 2-week faculty development program on data science and scientific computing. This program is jointly organized by Central University of Punjab, Purima University Jaipur, Nexus University South Africa, Baba Farid College Bathinda, and Methtech Thinking Foundation. So once again, thank you to all the participants who show your interest in this faculty development program, and we are really thankful to today's speaker for your valuable and informative session. Thank
you,
you to all.
Thank you.
Thank you to all.
Thank you.
Thank you, sir.
Mhlobo wami once more, ndicela undifakele usenqu apha, ndingu-admin khona.